Welcome back to the class. So in this class, we'll be discussing constraint optimization. What do you mean by a constraint optimization? As on given that function that is z as a function of x and y. Let's say we are given this function and we are asked to optimize this function. Optimization implies optimization implies either minimum, that is minimization or maximization of a function. So we have to optimize a function. It can be to minimize a function or to maximize a function. So for example, there are functions we maximize in economics and there are functions we minimize. For example, we maximize output function, we maximize revenue function, while we minimize cost function, expenditure function, we minimize those ones. Okay, wherever you hear the word optimization, so it could either be minimization or maximization of a function. But here, we are not only asked to optimize or maximize or minimize, but subject to a particular equation known as a constraint. So let's say we are given a constraint. And the constraint is a constraint. Okay. Let's say the constraint is given as ax. That's a times x plus b times y, then equals to k. This is a constraint. That is, we are asked to optimize the function. Okay, given the fact that the product of this plus the product of this is equals to this. So where a and b, a b and k are constants. They are constants. Okay, and the variable we have to optimize are x and y in this function. So how are we going to do that? We have to optimize subject to this. Okay, so in other words, we want to optimize this function subject to the constraint ax plus by equals to k. So what we are going to do is that is to optimize this function, we are going to set up what we call a Lagrangian function. That is, we have to set up a Lagrangian function. So it can also be written as this Lagrangian function, okay, as the case may be. So most of the time we use L to indicate that Lagrangian function will be equals to the function we are asked to optimize will come first. This is the function we are asked to optimize subject to will come later. So the function we are asked to optimize is this. So we are going to write it first. So that's f of x and y. Then we are going to introduce what is known as a constraint parameter. So usually we use lambda. Okay, that's something that is only another that we can use. We can also use mu. Okay, but the one that is commonly used is lambda. So we are going to introduce that constraint parameter. So I'm using lambda. Okay, whether I'm going to introduce plus sign before the lambda or minus or minus lambda, it depends on the arrangement of this constraint. Okay, if I want to start with k while taking other side of equation 2 to go and make k, if I want to do that, so the sign before k, that is the sign in the front of k, is plus. So this is what I'm talking about. If I say plus lambda, okay, so I'm going to open the bracket, then I'm going to write k first. Okay, then when I take other components to the other side. For example, it's going to be, I'm going to take ax to the other side, so it's going to be minus ax. Then I take the other one to the other side, I have minus by. Okay, so another way of setting up this function is by saying L equals, so this same thing xy. Then if I want to use minus lambda, so is it minus lambda? Okay, meaning that I want to leave this here. I'm taking k to come here. If I take k to come here, okay, so the sign of k will becomes minus. That is why I'm having minus here. Whatever sign that k takes, that is what sign that this constraint parameter will take. So minus lambda, so I have ax plus by minus k. Okay, so either of the two is correct. So I'm going to get the same value for this. Okay, now you can try that, but I want to stick to the first one. Okay, because I'm comfortable with that one. Okay, now, so this is what is known as a Lagrangian function. So the first thing I'm going to do now is that I'm going to find the first order condition. Okay, right? Derive the first order condition with respect to each of these variables, variable x and variable y. So in other words, I'm going to add that is the L, the x. So there is the partial derivative of this L, this whole function with respect to x. So if I do that, that is going to be equals to the derivative of this function with respect to x. If I use f of x to represent that, so I have x, y. So mind you, this f of x of its x, y. So it's simply equals to the partial derivative of this whole function, x and y dx. This is the same thing as this. Okay, so if I pull this, so I'm going to have, so I've differentiated this side. Now I have to differentiate this one. So I will differentiate this because this one has x component. So if I differentiate this one, so I'm left with y. K does not have x, it becomes 0. This one goes away. So I'm only out with, so differentiation of the, I'm only left with this a. So if I differentiate ax, so I'm going to have a. The sign, don't forget the sign minus a. So it's going to minus a multiplied by what I have outside. That's minus a lambda. So it's going to be minus a lambda. So, and I'm going to set this to 0. Okay. The second one, I'm going to do that too. So I'm going to have the L dy. So I'm differentiating with respect to y now. So I'm going to have f of x of y. Then I have x y. Then now I'm going to differentiate with respect to y here. This becomes 0. So if I differentiate with respect to this, I'm going to have minus b. Minus b multiplied by lambda is going to be minus b lambda. That is 0. Then thirdly, I'm going to find the partial derivative of L with respect to lambda itself. So if I differentiate with respect to lambda, so I'm going to have, if I differentiate lambda, it becomes 1. So 1 times everything in bracket. So this will be k minus ax minus by. So then I set equal to 0. So I can call this equation 1. Let me call this equation 2, 3, and 4. Okay. Now, these are the equation I'm going to solve. Okay. So I'm going to solve equations 2, 3, and 4. Okay. There are two ways of solving this problem. Okay. So the first approach, that's method 1. Method 1. Okay. What I'm going to do here is that we are going to make lambda the subject of the formula in equation 2 and 3 and set the result equal. So, for example, now from equation 2, from equation 2. So this is my equation 2. I have f of x, f of x, xy minus a lambda is equal to 0. So then if I make lambda is solve a formula, so I'm going to have f of x, y, then I have a lambda, okay, this will be equal to f of x, okay, then I have over here equal to lambda. So I can call this equation 5. So likewise from equation 3, I will do the same thing. So I'm going to have f of yx, then I have y, then I have minus b lambda equals 0. Then I have fy, then I have fy, okay, so equals b lambda. Then I have, if I make lambda is our formula, I have this xy, then this over b equals lambda. So the first approach is what? Just set, that is equate lambda to lambda. If I'm to equate lambda to lambda, that is lambda equals lambda. So in other words, I'm going to have f of x, x of x, y over a, then equals to f of y, then xy over b. Okay, so what am I going to do? The next thing is to cross multiply. If I cross multiply, I'm going to have x of it, I have xy, okay, equals, sorry, this is b, okay, then this multiplied like this, I have a of y, so I have xy. So this is what I'm going to solve. So here, when I solve this, I'm going to make either x or y the subject formula and substitute into equation 4. So that will give me the value for x, y, and I'll be able to solve determine the value for lambda too.